The ninth and final Gauss-Markov assumption is is sounds pretty complicated, but I'm going to give you some examples. And what it is it states that there's no autocorrelation. No autocorrelation means that there's no correlated residuals between any two levels of our predictor. Okay, now that sounds very complicated, but let me go through some scenarios. First, let's start with cross-sectional designs, where we have just one time point and we have multiple predictors. We're interested in identifying whether there is a significant relationship among our between our predictors and our dependent variable. But what happens if in our cross-sectional design we have some people at some level that will influence, being at that level influences the level of others. Okay, so let's think about what that might be. Well, if we randomly assign people to two treatments, one of two treatments, and the one treatment is a treatment where most of the participants really sought after, and then the other is let's say treatment as usual or a wait list. And after assignment, the people who did not get assigned this sought after treatment may have contact with those people who do. And what we get is the potential for a compensatory rivalry, where an individual looks over and maybe one of the people is really good at selling why this treatment is awesome. So what you get is you get a carryover effect where some observations, namely those people in the treatment group, influence those people who are not in the treatment group. And when that happens, what we have is we have an influence in the residuals, like how far off are we in our prediction model, where some level influences some level of our predictor, namely this treatment group, influences another level of the treatment group. And when that happens, we have an autocorrelation. Now, autocorrelations in cross-sectional designs are rare, and the example that I just gave you is somewhat contrived, but compensatory rivalry may come about. And the way we test for that is typically we'd use a statistical test like the Durbin-Watson test. But Durbin-Watson is most specifically designed to test autocorrelation in time series or repeated measures where we have repeated observations. And here's where autocorrelation becomes much more sensible. What happens when we make an observation at time 1 and that residual, where we don't predict very well, correlates to the residual at time 2? And why would that be? Well, we expect there to be a time effect when we're observing some variable over time. So one of our predictors is time. And one level of time, time 1, will produce residuals. And one level of time 2 will produce residuals. Now, when those residuals are correlated, it typically means that there is some artifact that, and we expect this anyway, there's some artifact that carries over that is beyond just time. And that could lead to maybe some individual differences. So if you parse this out, you may be able to include relevant variables that eliminate the autocorrelation. But it's usually that you're using the wrong tool for perhaps the right question. And ordinary least squares is horrible when you have situations in which there's potential for autocorrelation. For one, this is an assumption that there can be no autocorrelation, because what happens is it creates inefficient estimates, and it biases not just the parameter estimates. Parameter estimates may be biased, but not necessarily so, because it can be positive or negative. But most importantly, that it affects the standard errors, and then directly, as a result of that, affects the hypothesis testing. So autocorrelation, when you have correlated residuals among different levels of the same variable, right? So if time is a predictor, the residual for time 1 is correlated with the residual of time 2, ordinary least squares is not a reasonable tool to use. And you can assess that using Durbin-Watson test. There are some problems with that as well, and we'll go through that during our homework assignments in class. But what you'll find is that there are much better tools that are well suited for autocorrelation, and those include time series analysis or linear mixed effects models where you can model the correlated residuals. And there are all sorts of ways in which the residuals can be correlated, so you can model them in different ways. But ordinary least squares assumes that the correlations are 0, and so there's no way to model them. So this final assumption, there's no code that I've written, mostly because it's really difficult to create these things. And this is more conceptual, and it will be rare for cross-sectional data. And if you have repeated measures, you use the Durbin-Watson test to assess the potential for autocorrelation, or sometimes referred to as serial correlation. And if there's an autocorrelation, then you're best off selecting an alternative model. This wraps up the assumptions. I'm going to follow it up with a total summary along with a video about the assignments for the in-class assignments for this week. So stay tuned for the final video. Thanks.